It's amazing to think, really, that behind every seemingly simple online interaction, whether it's buying something, sending an email, or even just scrolling through social media, there's this hidden, incredibly complex battle going on against fraud.
Oh, absolutely. And the techniques these fraudsters are using are becoming so advanced, it's almost like a constant arms race.
Exactly. And that's what we're diving deep into today. We're looking at how artificial intelligence, specifically transformer models, are being used to detect fraud hidden in plain sight within text.
It's really fascinating. It's kind of like we have a front row seat to this ongoing technological battle through the insights we have access to today.
Right. And our goal today is, to go beyond just the buzzwords and all the hype and really break down what it takes to use these cutting-edge AI tools effectively.
Yeah, to get into the nitty-gritty, we're going to uncover the specific challenges, the innovative solutions that are being developed, and really the crucial considerations you have to make when you're trying to, well, essentially outsmart these increasingly clever fraudsters.
Because it's clear from what we've been looking at that it's not just about, applying some standard AI solution and calling it a day.
Right.
It requires a much more nuanced and adaptive approach, really tailored to the specific nature of how fraud manifests in text.
You hit the nail on the head there. It's a completely different ballgame.
So let's unpack that a bit. The research we're diving into highlights how dealing with fraudulent text poses unique challenges compared to, just your typical text analysis.
For sure.
One of the first big hurdles that jumps out is this concept of deliberate obfuscation. And I mean, we're not just talking about simple typos here.
Right, right.
We're talking about fraudsters actively and intentionally trying to disguise their intent to make it harder to detect.
It's really quite deliberate and strategic. What we're seeing is like the calculated use of slang, code words that might seem harmless on their own, but actually in the context of fraud, they take on this whole other sinister meaning. And then you have the intentional misspellings, like using key at YPOW instead of the correct spelling. It's all very calculated to try to bypass the more simple detection systems.
It's like they're trying to create their own secret language almost.
In a way, yeah. It's a way to fly under the radar.
Right, and this creates a really complex input space for these models to deal with. And as the research points out, even with all their power, even these transformer models with their huge number of parameters can really struggle to make sense of this intentionally distorted data.
It's like trying to find a needle in a haystack, but the needle keeps changing shape and the haystack is constantly moving.
Yeah, that's a great analogy. And you can imagine, for our listeners, how the sheer number of potential ways fraudsters can phrase their schemes just explodes when you add this layer of obfuscation.
Absolutely. It's a combinatorial nightmare.
And that makes it incredibly hard for the models to learn, to pick out those consistent patterns, those telltale signs that something's not right.
It's all about hiding in plain sight.
Then on top of that, you have the ongoing issue of labeled data, which, as our source emphasizes, goes far beyond just not having enough examples to work with.
It's not just about quantity, it's about the quality and representativeness of that data as well.
Exactly. Are we actually capturing the full spectrum of techniques that these fraudsters are using out in the wild?
That's the million-dollar question, because in fraud detection, we're often lacking what we call adversarial examples. And those are basically examples that really mirror the subtle, ever-evolving tactics that these fraudsters are using to try and slip through the cracks.
It's like training for a fight, but you've only ever sparred against one type of opponent.
Exactly. You might be well prepared for that specific opponent, but then, you step into the ring and it's a completely different fighting style.
Right. You're caught off guard. And then on top of that, the labels we do have, they might be skewed, they might be outdated, reflecting past fraud trends that are no longer relevant.
Because fraudsters, they are constantly adapting. They're always coming up with new methods. So our training data, it can become obsolete very quickly.
Yeah, it's like trying to navigate with an old map that doesn't show the new roads or the detours.
Exactly. You're bound to get lost.
So we've got this challenge of, constantly evolving fraud tactics. The language is changing. And our models need to be trained on data that reflects that constantly shifting landscape.
It's a moving target.
It really is. Now, moving beyond the data itself, the source material really dives into the inherent complexity of these transformer models, particularly when we talk about real-time fraud detection. And latency, it's identified as a major obstacle.
And it's fascinating because here you have this tension between power and speed. Transformer models, they're amazing at understanding context, which is absolutely crucial for, really picking up on those subtle cues of fraud in text.
Yeah.
But their autoregressive nature, meaning they kind of process data sequentially, predicting one element at a time, it can introduce delays,
Right.
especially when you're dealing with longer pieces of text or when you have multiple processing steps chained together. And in a real-time system like fraud detection, every millisecond counts.
You can't have someone waiting, an unreasonable amount of time for their transaction to go through while the system tries to make a decision.
No, absolutely not. It has to be seamless.
Right. The person at the checkout counter is going to get pretty impatient.
Exactly.
Now, the source mentions some pretty interesting techniques to try and address this latency issue, like dynamic batching and experimenting with sparse attention mechanisms. Can you break those down a bit for us in terms of how they actually help?
Sure. So dynamic batching, it's all about efficiency. You're basically grouping together text sequences that have similar length, which allows the system to, better utilize the parallel processing capabilities of the hardware. And that's really critical when you need those super fast response times.
Okay, that makes sense.
Then you have sparse attention mechanisms, which is like a level up in terms of sophistication. So instead of the model needing to look at every single part of the input sequence to make a decision, it can actually focus its attention on like the most relevant parts, which reduces the overall computational load.
Kind of like instead of reading a whole document word by word, you quickly scan it for the key points.
Exactly, like a targeted approach.
And then, of course, there's the hardware side of things. The interviewee specifically mentions things like, using GPU-accelerated inference on platforms like TensorRT. So for someone who's maybe not as familiar with the technical details, what's the takeaway there?
So basically, it's about using specialized hardware, GPUs, that are really, really good at the kind of complex math that these AI models need to do. And then platforms like TensorRT come in and further optimize those models to run even faster on that hardware. So it's kind of like a 1-2 punch to really get that speed boost without sacrificing the model's accuracy.
So you're getting the best of both worlds.
Exactly, striking that balance.
So we've got these incredibly powerful models.
Yeah.
We've got this intentionally misleading data.
Yeah.
We've got these limitations with labeled data.
Yeah.
And the need to do all of this at lightning speed in real time, it really paints a picture of a very challenging environment.
It is. It's a high-stakes game.
It is. Now let's shift gears a bit and talk about how we actually train these models effectively. And specifically, how do we mitigate overfitting, which I imagine is a major concern with such complex models and the data limitations we talked about.
Oh, absolutely. It's a constant concern. And as our expert points out, the standard techniques we often use to prevent overfitting, things like dropout and weight decay, they kind of hit a wall in this context. And even something that seems like it would be helpful, like SINN replacement to try and expand the training data, it can actually backfire spectacularly.
Yeah, because if a fraudster intentionally misspells a word, like payment, Pete at Ament, to try and get around those filters, you wouldn't want to just correct that during training.
No, not at all, because then you're basically training the model to ignore the very things that might be a sign of fraud. It's like teaching a security guard to ignore someone wearing a disguise.
Right. You're removing the very thing that they need to be looking for.
Exactly. You're training them to see what the fraudster wants them to see.
So you need these more advanced, more targeted strategies.
Absolutely.
And the source mentions a couple of really interesting ones.
Yeah.
Adversarial training using FGSM, that one really caught my eye. It sounds like you're proactively trying to make the model more resilient.
It is. It's like giving the model a good workout, so it's ready for anything.
Okay, I like that analogy.
So FGSM stands for Fast Gradient Sign Method. And essentially what you're doing is creating these slightly altered versions of your training data. Kind of like, little traps specifically designed to fool the model.
Okay.
And by training the model on these intentionally tricky examples, you're basically forcing it to learn these more robust and generalizable representations. So it's less likely to be fooled by those minor variations, those little tweaks that fraudsters might use.
So it's like it's seen all the tricks, it's ready for whatever they throw at it.
Exactly. It's not easily fooled.
The source also really emphasizes the importance of using time series stratified splits for cross-validation. Now, why is that particular way of splitting the data so crucial when we're talking about fraud?
Because, as we said before, fraud patterns, they're not static. They're always changing over time. So if you just randomly split your data into training and validation sets, you're basically taking a gamble. You might end up including some future fraud tactics in your training data, which would give you a false sense of security.
Like the model thinks it's doing great, but it's only because it's already seen the answers to the test.
Exactly. So what time series stratified splitting does is it makes sure that your validation sets always come from a later point in time than your training data. So it's a much more realistic test of how well the model will actually perform on those new, unseen fraud attempts.
So you're accounting for that concept drift, that constant evolution.
Precisely. You're preparing the model for the future, not just the past.
And finally, when it comes to training, they talk about this concept of domain adaptive pre-training on fraud-specific data sets.
Yeah, that's a really powerful technique.
It almost sounds like you're giving the model a head start.
That's a good way to put it. Instead of starting from scratch, you're basically pre-training the model on this massive collection of text that's specifically related to fraud, even if it's not explicitly labeled as fraudulent or not. So it gets to learn the language of fraud, the vocabulary, the entities, the style, all of that, before it even sees your labeled fraud data.
So it's like it's gone to fraud school before it even starts the real training.
Exactly. It's already got a foundation in the language of fraud.
That's a great way to put it. So we've talked about these specialized training techniques.
Uh-huh.
Now, let's get into the data itself. How do we prepare this raw text data to be fed into the model? I know there's this idea of basic cleaning, removing punctuation, that sort of thing, but the research suggests that for fraud detection, you need a much more nuanced approach.
Absolutely. Basic cleaning is like the bare minimum, is just the starting point. What our expert emphasizes is that you need to go deeper. Like, you need to remove things like HTML tags and non-standard Unicode characters, which can actually be used in encoding attacks to try and trip the system.
Oh, interesting. So even those seemingly innocuous things can be weaponized.
Absolutely. You have to be very careful.
And then there's this idea of aggressive entity masking, redacting things like personally identifiable information and suspicious domain names. What's the rationale behind that?
So there are a couple of reasons for that.
Okay.
First, it's about protecting privacy, complying with regulations like GDPR. You don't want the model to be learning and potentially exposing sensitive information.
Right, of course.
But secondly, it's also about encouraging the model to focus on the underlying linguistic patterns and the context, rather than just memorizing specific names or domains that might change frequently.
So you're teaching it to be more adaptable, to look for the deeper signs.
Exactly. You're teaching it to understand the intent behind the words, not just the words themselves.
And the interview also brings up this challenge of out-of-vocabulary, or OOV, words,
Yeah.
which apparently are pretty common in this user-generated content, this fraudulent content.
They are. They are. It's a real headache.
So how do you effectively handle those?
So you need to get a bit more creative with your tokenization. So while pre-trained models like BERT have their own built-in tokenizers, the suggestion is to supplement that with custom dictionaries that can recognize these non-standard spellings, these creative obfuscations that might otherwise trip the model up.
It's like you're giving it a decoder ring to understand the secret language of fraud.
Exactly. You're expanding its vocabulary.
Now, this concept of engineering fraud-specific stop words,
Yeah.
that was particularly fascinating to me. Can you give an example of how that might work?
Sure. So stop words are those common words that, we often remove during text processing, like they and n, that kind of thing.
Right, the little words that don't really carry much meaning on their own.
Exactly. But in the context of fraud, certain words that are normally harmless, they can actually become like red flags when they're used a lot or in specific combinations. Like, imagine suddenly seeing a huge spike in the use of words like free trial or bonus in financial communications. That might signal something fishy, right? So by treating these contextually suspicious words as stop words, you can help the model zero in on those more important parts of the text.
So it's not just about removing words that are always unimportant, it's about being strategic and considering the context.
Exactly. It's about tailoring your approach to the specific domain of fraud.
So we've gone through, these specialized training techniques, this tailored data preparation.
Yeah.
And the next big thing the interview delves into is multitask learning, and specifically integrating an auxiliary task like anomaly scoring. And it sounds like this is a way to, bring in additional information to kind of enrich the main fraud detection task.
It is. It's like giving the model a wider perspective. So as they explain it, this anomaly score, it's derived from these behavioral and contextual features. Things like unusual login times, changes in device fingerprints, suspicious IP address patterns, all these things that aren't actually in the text itself.
It's like the digital fingerprints of the user.
Exactly. And the idea is to feed that information into the model alongside the text as kind of a secondary objective.
So it's getting a more complete picture.
Exactly. It's not just looking at the words, it's looking at the behavior, the context, the whole story.
Now, the source raises a good point, though, which is how do you prevent this auxiliary task from actually messing with the main fraud detection task?
Right, right. Because there's always that risk.
This idea of negative transfer.
Yeah, if the auxiliary task is too different, or if it conflicts with the main task, it can really confuse the model and actually make its performance worse.
So it's like you're trying to teach someone two things at once, but they're so different that they start to get them mixed up.
Exactly. They can't keep the information straight.
And the expert mentions a couple really clever ways to address this.
Yeah,
One is this dynamic uncertainty weighting. Can you explain that a bit?
sure. So with dynamic uncertainty weighting, the model actually learns to adjust how much importance it gives to each task based on how confident it is in its predictions for each one. So if it's struggling with the auxiliary task, it might focus more on the main task and vice versa. It's like it's constantly reevaluating its priorities.
So it's very dynamic, very responsive to what's working and what's not.
Exactly. It's like a self-correcting system.
And they also talk about gradient surgery, which sounds pretty intense.
It's a bit more on the technical side, but essentially it involves modifying the gradients, the signals that guide the model's learning process.
Okay.
And the goal is to make sure that the updates from the auxiliary task don't end up working against the updates from the main fraud detection task. So if the gradients are kind of pushing the model in opposite directions, gradient surgery can kind of step in and smooth things out.
So it's like you're making sure that both tasks are pulling in the same direction.
Exactly. It's all about harmony and synergy.
Now let's talk about another critical aspect of any fraud detection system, especially when you're potentially flagging someone's activity as fraudulent.
Right, right.
Interpretability, being able to understand why the model made a certain decision. But as our source points out, the really computationally intensive methods might not be practical when you're talking about these massive transformer models operating in real time.
Yeah, it's a tough trade-off. While methods like A-shape-E and LIME can provide very detailed explanations, they can be just too slow and resource-intensive to use in a live system where decisions need to be made, like, instantly.
Right.
So you need these faster but still reliable ways to kind of peek inside the black box and understand the model's reasoning.
And the interview talks about some of those faster techniques like integrated gradients and saliency maps. Can you briefly touch on what those methods tell us?
So integrated gradients, they aim to quantify how much each input feature, in this case each word in the text, contributed to the model's final prediction. And they do that by kind of tracing the path of the gradient from a baseline input to the actual input.
Okay.
Saliency maps, on the other hand, they provide a visual representation, kind of like a heat map, highlighting which parts of the text were most important in the model's decision-making process.
So it's like you're seeing which words really caught the model's attention.
Exactly. It's like highlighting the smoking gun in the text.
That's a great way to put it.
And both of these methods, they give us a glimpse into the why behind the prediction, but without that heavy computational burden.
Okay, so they're more practical for a real-time environment.
Exactly. They strike a balance.
Now, there's also this mention of counterfactual analysis frameworks. What's the value of being able to ask these, like, what-if questions of the model?
So counterfactual analysis lets you explore how changes to the input would affect the output. Like, what if this user had used a different email address? Would the model still have flagged this transaction as suspicious?
I see.
And by doing that, you can gain insights into how sensitive the model is to different features. You can really understand what's driving its decisions.
So you're kind of testing its logic, seeing if it's making decisions based on the right things.
Exactly. You're validating its reasoning process.
Now, going even deeper into this interpretability, the interview touches on analyzing those attention mechanisms, but not just looking at the raw numbers.
Right.
How do you actually quantify their contribution in a meaningful way?
So it's about going beyond those attention weights, which just tell you how much the model is focusing on different parts of the text.
Right.
It's about trying to understand, is the model's attention actually aligned with the features that are important for the prediction? So you can use techniques like integrated gradients to see if the parts of the text that the model is focusing on are actually the parts that are driving the decision. And if they're not, then that might be a sign that something's not quite right.
So it's kind of like a sanity check, making sure the model is focusing on the right thing.
Exactly. You're making sure it's not getting distracted by irrelevant information.
And finally, when it comes to interpretability, The interview stresses the importance of having this robust audit trail, especially with all these regulations like GDPR that require you to be able to explain your decisions.
Absolutely. It's not just about understanding the model internally, it's about being able to justify its decisions to the outside world.
Right, to be transparent.
Exactly. So you need a clear record of what the model predicted, what factors influenced that prediction, and ideally some insights from those interpretability techniques we talked about. It's all about accountability and building trust.
It's like having a paper trail to show your work, basically.
Exactly. You need to be able to show your reasoning.
Now, a system that's tasked with identifying fraud in real time, it needs to be incredibly efficient.
Oh, yeah. Speed is of the essence.
And our source goes into the challenges of scaling these complex transformer models without compromising their accuracy.
And that's where you have to get smart about optimizing both the model itself and the infrastructure it runs on.
Okay.
The interviewee talks about techniques like knowledge distillation and quantization. Can you kind of break down what those are and how they help with scalability?
Sure. So knowledge distillation, it's almost like an apprenticeship. You have the smaller, more efficient model, the student, that's trained to mimic the behavior of a larger, more complex model, the teacher. So it's like passing on the knowledge, but in a more compact and efficient package.
It's like a master craftsman teaching their apprentice the tricks of the trade.
Right, passing on the wisdom.
Exactly. And then you have quantization, which is about reducing the precision of the numbers that represent the model's parameters. So it's like shrinking the file size without losing too much information.
So you're making it leaner and meaner.
Exactly. It's all about optimization.
And the source gives some really concrete examples, like pruning non-critical attention heads, basically getting rid of those parts of the model that aren't pulling their weight.
Exactly. Streamlining the model.
And using variants like the stillBERT, which is a smaller, faster version of BERT that's specifically designed for this kind of real-time inference. And of course, they mentioned Tensor again, which we talked about earlier.
Yeah, that's all about getting those models running as smoothly and efficiently as possible on that specialized hardware.
Now, beyond optimizing the model itself, they also talk about using a microservices-based architecture with Kubernetes. Why is that kind of approach so beneficial for scaling a fraud detection system?
So a microservices architecture, it's like breaking down a big complex system into these smaller independent modules that can be developed, deployed, and scaled separately. And Kubernetes is like the conductor that orchestrates all of these modules, making sure they work together seamlessly.
So it's like having a team of specialists, each handling a specific part of the task.
Exactly. It's a much more agile and scalable approach.
And there's this idea of a model cascade that I found really intriguing. Using a fast, rule-based filter for that initial screening before only sending the more ambiguous cases to the full transformer model.
That's a really smart way to balance speed and accuracy. You're basically using a simpler, faster method to catch the low-hanging fruit, the cases that are clearly fraudulent or clearly legitimate, and that frees up the more complex model to focus on those trickier cases that require a deeper analysis.
So it's like a triage system, sending the most critical patients to the specialist.
Exactly. You're prioritizing your resources.
Okay. So now, given that fraud is constantly changing, how do we make sure that our detection system doesn't become obsolete? How do we keep it effective over time?
That's where data drift detection comes in.
Right.
And the expert really stresses the importance of being able to distinguish between two types of drift. Data drift, where the statistical properties of the data are changing, and concept drift, where the underlying relationship between the inputs and the output, whether something is fraudulent or not, that relationship is changing.
And they mention specific algorithms like the Kolmogorov-Smirnov test and ADWN. What are those designed to detect?
So these are statistical tests that are really good at picking up on subtle shifts in the data patterns over time.
Yeah.
The Kolmogorov-Smirnov test, it can compare two data sets and tell you if they're likely from the same distribution. And ADWN, which stands for adaptive windowing, it looks at a sliding window of recent data and can detect significant changes within that window.
So it's like you're constantly monitoring the data for any signs of change.
Exactly. You're looking for those early warning signals.
And there's also this idea of setting up an adversarial validation framework specifically to detect adversarial drift, which is kind of like a preemptive strike against those evolving fraud tactics.
It is. It's like setting up a honeypot for fraudsters. You basically train a separate classifier whose sole job is to distinguish between old data and new data. And if that classifier starts getting really good at its job, that's a red flag.
It means the fraudsters are changing their tactics.
Exactly. They're adapting, and you need to adapt as well.
And the interview also emphasizes the importance of dynamic retraining cycles. Not just retraining on a fixed schedule, but actually retraining based on how the model is performing or when you detect these shifts in the data.
That's a much more agile and responsive approach. You're not wasting time and resources retraining when you don't need to.
Right, you're reacting to what the data is telling you.
Exactly. You're letting the data guide your actions.
And finally, they talk about the importance of preventing data poisoning.
Yeah, that's critical.
Making sure that your training data hasn't been tampered with, that it's clean and trustworthy.
Because if you're training your model on bad data, you're going to get a bad model. It's like trying to bake a cake with spoiled ingredients.
Right, it's not going to turn out well.
Not at all. So you need those strict data sanitization protocols to filter out anything suspicious, and version data lakes to keep track of all the changes to your data so you can always roll back to a clean version if you need to.
So it's like having a backup, a safety net.
Exactly. You're protecting your most valuable asset, which is your data.
Okay, so we've covered a lot of ground here. And finally, the interview gets into this idea that, fraud is increasingly becoming multimodal. It's not just about text anymore.
Right.
But they also make the point that just combining all those different types of data together isn't necessarily the best approach.
No, not at all. Just throwing everything into the pot and hoping for the best. It rarely works out.
So they propose this hybrid architecture that uses separate encoders for different data modalities,
Right.
like text, tabular data, temporal sequences, and then fuses those representations together using these cross-modal attention mechanisms.
Yeah.
Can you explain a bit more about what those are and why they're so important?
Sure. So different types of data have different characteristics, right?
Right.
Text is very different from tabular data, which is very different from a time series.
Mm-hmm.
So the idea is to use the right tool for the right job. You might use a transformer model for the text, a different type of encoder for the tabular data, and maybe something like a recurrent neural network for the temporal sequences. And then those cross-modal attention mechanisms, they act like bridges, allowing the model to see how those different pieces of information relate to each other, how they fit together to paint the full picture of the user and their activity.
So you're not just looking at each piece of data in isolation, you're seeing how they all connect.
Exactly. It's like putting together a puzzle. You need all the pieces to see the full image.
And they specifically mention models like Transformer XL for capturing those temporal dynamics. What's the advantage of using that kind of architecture?
So Transformer XL, it's a more advanced version of the Transformer model that's really good at handling those longer sequences of data and understanding how things change over time. So in the context of fraud, it can be really powerful for looking at a user's behavior over time, like their sequence of logins, their transactions, all that, and seeing if there are any subtle anomalies that might indicate something's wrong.
So it's like you're looking at the whole timeline of their activity, not just a snapshot.
Exactly. You're looking for those patterns that only emerge over time.
Now, to make sure this multimodal approach is scalable, they talk about normalizing each data type separately before you combine them, and also using these robust imputation strategies to handle missing values. Why are those steps so important?
So normalization, it's all about making sure that features with different scales don't end up unfairly influencing the model.
Right.
Like you wouldn't want a feature that has a huge range of values to completely overshadow a feature that only has a small range of values.
Right.
And imputation, it's about dealing with the fact that real-world data is messy.
Uh-huh.
You're always going to have missing values.
Right.
So instead of just throwing away those data points, you can use techniques like learned embeddings to make informed guesses about those missing values, which helps preserve the information and prevents data loss.
So you're being smart about how you fill in those gaps.
Exactly. You're using all the information you have to create the most complete picture possible.
So it really sounds like this intelligent fusion of multimodal data gives you a much more comprehensive and accurate understanding of potential fraud.
Absolutely. You're combining the power of different AI architectures tailored to different types of data and then bringing it all together to create a much more robust and resilient system host.